All right, calculus people, today we're going to go into our last kind of integral approximation method. We would call this a numerical method for integrals. And this is going to be called the trapezoidal method for reasons which you should probably know by now. So let's go ahead and get started with the trapezoidal method. Velociraptor in real life was a genus of a dromaeosaurid theropod dinosaur from the late Cretaceous period, which inhabited what is now Mongolia, the Mongolia-China border, with other unique dinosaurs. Velociraptor was no bigger than a wolf, and with its feathers it bore a very bird-like appearance that would make it much different than the velociraptors that you saw in the films. They were more like a flightless hawk. They had a long claw, the terrible claw from the, we'll talk about where that comes from, on their second toe of both feet, 8 centimeters long, and was probably used as a weapon, plunging into the flesh of its victims, causing deep wounds. Ooh, that is... wow. Okay, in the Jurassic Park universe, the term Velociraptor is applied to another genus, to the genus of another dromaeosaurid dinosaur known as Deinonychus. That's where terrible claw comes from, Deinonychus. The films, like the novels, follow the unusual taxonomy created by Gregory Paul, who believed that Deinonychus, as well as a few other species of dromaeosaurids, could be classified under the genus Velociraptor. So what we see in the film is not really a Velociraptor, but something closer to a Deinonychus. Okay, in the 2015 entry of the Jurassic Park film franchise, Jurassic World, finds the behavior researcher Owen Grady training 4 velociraptors. They get called the Raptor Squad, which I think is just adorable, the Raptor Squad. Their names are Blue, Charlie, Delta, and Echo. And they maintain a tenuous relationship with Grady, who calls himself the Alpha. But yeah, right, huh? And have been hand-reared by Grady since birth, which, you know, I guess that's kind of cute and cuddly, if cute and cuddly means rip your face off and eat you for lunch. Exploration. Echo sprints to a lamb carcass under Grady's supervision. Grady records Echo's velocity and time as she accelerates during this experiment, and here's the data that he gets. At 0, the velocity of Echo is 1. At 2, we got 7.5. 3, we got 9. And 5, we have 10. The data suggests the coordinates 0, 1, 2, 7, 5, 3, 9, and 5, 10. Complete plotting the rest of these points. Okay, let's plot the rest of these points. At this point, if we wanted to estimate the velocity of Echo's velocity, the integral of Echo's velocity, we would be using rectangular methods like LRAM, RRAM, or even MRAM. But today we're going to approximate this method, which is not a Riemann sum, but gives a fairly accurate estimation to the integral when compared to rectangular sums. So this is another method, and of course we already said that it's a trapezoidal method. So if you look at the first 4 points here, we can draw ourselves a trapezoid. Let's draw that trapezoid. Just connecting those first 2 points gives us a trapezoid like that. And yeah, we can find the area of that trapezoid. We've done this before in the beginning of this chapter. I think it was the water tank problem for the Roseland apartments. So what is the area of this trapezoid? Well, this base right over here, that has a height of 1. This base on the right side, that has a height of 7.5. And the height of the trapezoid, which is really the base of the trapezoid, that's 2. And if I want to find the area of this trapezoid, of course, we're just going to put that into the area formula for trapezoids. And that gives me the area of that first trapezoid is 8.5. Now we're supposed to find the area of the remaining trapezoids. Now the second trapezoid has a height on the left side of 7.5, a height on the right side of 9, and a width of the delta x here of 1. So the area is 1/2 1 times 7.5 plus 8. 9. So that second trapezoid has an area of 8.25. Now going up to the third trapezoid, we'll do that in red. In the red trapezoid, the right side goes up to 9, the left side goes up to 9, the right side goes up to 10, and this delta x down over here is 2. This gives me the area formula 1/2 2 multiplied by 9 plus 10. That third trapezoid has an area of 19. Let's add all three of these trapezoids together. So the integral is approximately equal to 8.5 plus 8.25 plus 19, and that's 35.75. And the oversized flightless hawk sprints 35.75 meters in 5 seconds to get to the lamb carcass. How charming. So we're going to actually, now that we know what we're doing, we're just adding a bunch of rectangles, we're going to try to make this a little bit more, put a routine to this. So this is developed kind of in the same way that we developed our routines for rectangular methods. We're going to get a chart here. The first one is always the interval. The second one is going to be delta t, or across delta x. And then instead of the height, you're going to find the averages of the heights. Okay, that's because that's what we're doing. We're just finding 1/2 base 1 plus base 2. And then the area, you multiply the height and the average of the heights and then the base. Let's just go ahead and do it. Our first interval goes from 0 to 1. That's a delta t of 1. Sorry, we should read the context here, right? Oil is leaking out of a tanker, another leaking tanker. Oh, this is the same leaking tanker. The damage to the tanker is worsening as evidenced by the increased leakage per hour recorded in the table below. Use the trapezoidal method to approximate the amount of oil leaked in the first 5 hours. So we've got first intervals from 0 to 1. Delta t is 1. We're going to find the average of the bases, which is 50 and 70. So the average of 50 and 70 is 60. And so the area of that first trapezoid is also 60. The second trapezoid goes from 1 to 2, which gives me a delta t of 1. And we need to find the average of 70 and 97. That's 83.5. And the area of the trapezoid is 1 times 83.5, which is just 83.5. Okay, next trapezoid goes from 2 to 3. That has a delta t. 3 minus 2 is 1. To find the average height, we're going to do half of 136 plus 97. And the area is just 1 times 116.5, which is just 116.5. The last trapezoid, that goes from 3 to 5. This time we have a delta t of 2. To average the two heights, we have half of 136 plus 265, which is 200.5. And then now for the area, that's just 2 times 200.5, which is 401. Now we're going to put the whole thing together and add up all of the trapezoidal areas because we found the area of each individual trapezoid. So the integral can be approximated by 60 plus 83.5 plus 116.5 plus 401, which is all of the areas across the bottom of our chart. That's 661. So during the first 5 hours, the tanker leaked 661 gallons of oil. So I hope that little bit about how to use the trapezoidal method practically helped a little bit. There's a lot of similarities with how we do things for the trapezoidal or the rectangular methods. So let's take a look at the important ideas here for the trapezoidal rule. So the trapezoidal approximation is very similar. It shares a lot of common things with the rectangular approximation, except the shape is going to be a trapezoid instead of a rectangle. Instead of using the height on the left side or the height on the right side, you're going to use an average of the two heights. Under most circumstances, the trapezoidal approximation will give you a more accurate area than either the LRAM or RRAM alone. And as a final thing is, if you found LRAM and RRAM already, you can find the trapezoidal approximation just by averaging LRAM and RRAM. So the average of LRAM and RRAM is the same value as the trapezoidal approximation. Let's take a look at our Check Your Understanding. Here's another leaking oil tanker. You would think that oil tankers leak everywhere here in Ferraria's math class. During the time interval from 5 to 8 hours, the oil tanker's leakage rate was given below. Oh, this is the same oil tanker, just extending it out to 8 hours now. So first of all, we're going to use a trapezoidal method to estimate the amount of oil leaked. So let's go ahead and do that. We're going to do this interval by interval. So our first interval is going to go from 5 to 6. 5 minus 6 is 1. Averaging out the left side and the right side, we have the half of 265 plus 369. That's 317. And the area of that first trapezoid is 1 times 317, which is 317. The next trapezoid is going to go from 6 to 7. 6 minus 7 is 1, so delta t is 1. The average of the left side and the right side is half of 369 plus 516. That gives me 442. And of course the area is 1 times 442.5, which is just 442.5. The last trapezoid is going to go from h equals 7 to h equals 8. 7 minus 8 is 1. The average of the left and the right side is half of 516 and 720, which is 618. And then the area of the trapezoid is 1 times 618, which is just 618. Now if I want to approximate the integral from 5 to 8, I just need to add up all three of those trapezoids, which adds up to 1,377.5. Meaning that the oil tanker leaked 1,377.5 gallons from t equals 5 to t equals 8. Part B says to find an average leakage rate. So the average of anything in calculus is 1 over b minus a, integral from a to b of f of x. The average leakage rate from 5 to 8 is going to be the average of the L, because L is the leakage rate function, from 5 to 8. And of course we have an approximation for that integral. The approximation of the integral is 1,377.5. That evaluates to 459.166. So the average leakage rate is 459.166 gallons per hour. So there you have it. You guys have one more section to go to before we're ready for your chapter test. It's a little bit more on the trapezoidal method, and yeah, counting down to the end of chapter 6. Good luck to you, and we'll see you at the very next time here at the calculus.